the third part of the lesson today will be Newton's law of motion, or in our everyday language are known as the laws of Newton or Newton's law. And there are three, as you know, from, as I said, from the everyday life. As the very first law is known, so first law is known as the inertia law. Even Aristotle, when he was observing the world, he was thinking that what is, like, the big question that he had was, what is the natural state of an object? So, and through a very, now we know, very not difficult observation, he figured out that the natural state of an object is to be at rest. So the object stays at rest. Okay, when we see an object, it has the tendency to stay at rest. And then later on, Galileo was again tackling this question, and he was noticing that actually, if the object is moving, what is making the object to move is a force. So if you are exerting a force, then the object will start moving. But if it starts moving, then and there is no friction at all, not air resistant, no friction between the surfaces, then the object will keep moving as will keep moving with the same way as it started forever. So this is it is important, because the first law is saying that we know that, okay, we know that this, what is happening, what Galileo was saying, is now known as the uniform motion. The velocity doesn't change. The motion is the same at every fragment of the time. And someone is saying here that inertia is the property of an object that resists acceleration, that resists motion in general, not just acceleration. So inertia is resisting the motion. The object will stay at the state that it is at if no other forces. This is the first, the definition of the first law of Newton. Newton took all those searches, what Aristotle did and what Galileo did, and formulated the first law of motion, that the object will keep moving at the same way unless other forces is experiencing. So if the object is at rest, will stay at rest until a force is applied into that object. If the object is moving at a constant velocity, will keep moving at a constant velocity until another force is applied into the object. An object is moving at the same way that it started, unless other forces are applied into the object. So the second law of Newton, though, is saying when the object, when the object is moving with an acceleration, the acceleration is indirect proportion to the mass of the object. So in other words, as we know, in the world of physics, the second law is expressed like force net is equal to mass times acceleration. Let's stop a bit here. What is force net? What is this new concept that I am introducing it to you? Force net is or resultant force, you can see it in both ways. Usually it is force net. What force net is the vectorial sum of all of the forces that the object is experiencing. Whatever forces the object is experiencing. It is the vectorial force though. So when we did the free body diagram on all the other situations above, then we will add them vectorially, meaning that we will not just add the magnitude of them, but we will find the components. If it is a 2D or if it is a 1D, then we add and subtract with the add with positive and negative numbers. But let's say here is the vectorial sum of all forces that the object is experiencing. Okay, so now when that we have the free body diagram of the object, then what do? Is we draw X and Y axes on it, and then we say, okay, this is how we are adding them. Finding horizontal components, finding vertical components, adding all the vertical components and horizontal components, and then finding the horizontal component of force net, vertical component of force net, and finding what it is. So what does that mean? If we have a situation like this, let's suppose that we have an object with mass m equal, I will put a number now, 10 kilogram for simplicity. And then this object is tied with two strings. Easy. So string 1 is going up and string 2 is, let's not put the surface here. So string 2 is this one. So two people are tying this up with an angle of, on this case here, of let's say 35 degrees. Okay, so let's find now the force net that this object is experiencing. So those two ties, let's suppose that we have a person that is pulling here with a force of T1, with a force of 100 newtons, and this T2 is pulled up with a force of 120 newtons. And our job is to find what is force net that this object is experiencing. So in order to do that, we have to draw the free body diagram. So as we said on the second part of this lesson, the object of our interest is replaced by a dot. And then we have a force of gravity, which is the going down. But now we have two objects that are horizontal, okay? So we have a force of gravity. Let's add that. And we have a tension 1 that is going up. Tension 1. That is with a magnitude of 100 newtons. And tension 2 that is with a magnitude of 120 newtons at 35 degrees. Is the free body diagram clear? So now our job is to figure out what is the force net. So force net based on the definition that we just gave, is vectorial sum of all the forces that the object is experiencing. And in our case will be force of gravity, tension 1, and tension 2. Again, to emphasize here, we don't have an object that is on a surface, therefore we don't have force normal. All the forces that the object is experiencing are force of gravity, T1 and T2, okay? So since what we are doing here is we are adding vectors, then what we do is we just add vectors. So this is the horizontal, and here we have the vertical. We have all the forces that we are adding, force of gravity, all the vectors that we are adding, T1, T2, and when we are done, we say force net. So the horizontal component of force of gravity is equal to 0 because it is a force that goes down vertically. And the vertical component of force of gravity is negative. Now, always when you have a situation like this, imagine that you have X and Y axis right at the object. So this will be X or horizontal, and this will be Y or vertical axis. Okay. So now, since it is force of gravity is going down, then will be negative. Yeah, will be negative 981. Why? Because force of gravity is mass times acceleration due to gravity, and mass in our case was 10 times 9.81, so will be 98.1, sorry, 98.1 newtons. Okay? 98.1 newtons. And now we have tension 2. The horizontal component of tension 2 is equal to 0 because it's a vector that is going vertically up. And the vertical component will be positive, and it is positive whatever is the magnitude that in our case is 100. For tension 2, what do we have is a vector that is between south and west, and therefore we will have this vector here, tension 2, as a horizontal component, and this vector here as the vertical component. So then for the horizontal component is negative, and it is negative 120 times cosine. That is 100, which is 98.3. And in order to find the vertical component, we will use sine, and it is negative 68.8. Now, what do we do as in every vector when we work with operating with vector? We add the horizontal components and we add the vertical components to figure out what is the horizontal component of, in our case, force net, 98.3. And on this case will be negative 98.1 plus 100 minus 68.8 equals to negative 66.9. What this is telling us is saying that the horizontal component is negative 98.3 and the vertical component is a negative 66.9. So force net is a vector that starts at the starting point for the closed polygon one and end at the end point. And the magnitude of force net will be the square root of 98.3 squared plus 66.9 squared. 98.3 squared plus 66.9 squared, the whole thing square root. It is equal to 118.9. You can say 119. And the angle alpha will be inverse tangent of 66.9 over 98.3. So inverse tangent 66.9 over 98.3 equals to 34.2 degrees. So force net is equal to, you can say 119, just rounding it, at 34.2 degrees. And this is, what is it, south of west. Do you understand? It's simply adding vectors. So this is force net. And now, based on the second law of Newton, what do we have is mass times acceleration. If we go a step further here, and then I'm asking you, what is the acceleration for this particular situation? Then what do you have to do is acceleration will be force net over mass. Mass is a scalar quantity, yeah? So then this will be 119 newtons at 34.2 degrees south of west over mass, that is 10 kilograms. And then the acceleration will be 11.9 meters per second squared at 34.2 degrees south of west. Is it clear? Let's go back for one more moment to the second law of Newton that is saying force net is equal to mass times acceleration. So we said that force is a vector quantity. And we have emphasized that acceleration is a vector quantity as well. Mass, on the other hand, is a scalar quantity. Scalar means a numerical value. So what do you have in this relationship is a vector is equal to a scalar, a number, times another vector. From this relationship, straight from this relationship, we can say that force net and acceleration have the same direction. So if you know the direction of force net, then you know the direction of acceleration. Or if you know the direction of the acceleration, then you know the direction of force net. If I'm telling you in a question that the object is moving east with an acceleration 2.5 meters per second squared, then you in dynamics have to think that, okay, even force net is east in this particular situation. So if you know the direction of the acceleration, then you know the direction of force net. And if you know the direction of force net, then you know the direction of acceleration because they are the same. And this conclusion comes from what we have here in the second law of Newton, that you are multiplying a vector quantity, the acceleration, with a scalar. And the mass is always positive, so the direction doesn't change, it's not flipped. When you are multiplying a vector by scalar, then what do you see is another vector that has a different magnitude, but the same direction when the scalar quantity is positive and the opposite direction when the scalar quantity is negative. In our case, mass of the object cannot be a negative value. Therefore, force net and acceleration have the same direction. Is it clear? And from this relationship that we see here, mass times acceleration, it's drawn even the units of force. So the units for mass are international units for mass are kilograms. And the units for acceleration, as we said, are meters per second squared. So when you multiply those two together, what do you have is 1 Newton. Okay, those units that we talked initially is, so 1 Newton is equal to, let's not do this, not brackets. So 1 Newton is equal to 1 kilogram, 1 meters per second squared. Okay, well, because 1 times 1 is 1, so 1 Newton is equal to 1 kilogram times 1 meters per second squared. Okay. Now let's talk a bit about the third law of Newton, which is as important as the second law, because usually we just deal with the second law and then we kind of forget about the other ones, but without them, we cannot have the whole picture. So the third law of Newton is known as the action-reaction law. It's saying that every action will have the opposite reaction. So action, reaction. So this is saying that if you are pushing an object with 10 newtons east, the object is pushing you with 10 newtons west. So F12 is equal to negative F21. The force that object 1 is exerting on object 2 is equal to the opposite direction, but same magnitude with the force that object 2 is exerting at object 1. If you are pushing an object 10 newtons in the east direction, the object will push you back with the same magnitude, 10 newtons, in the opposite direction, west, because the opposite of east is west. If you are pushing an object with 15 newtons north, the object will push you back with 15 newtons, but now the opposite of north is south. Now, a question that I have for you is, okay, if we have two forces, so this is force that object 1 is exerting on object 2, and then the same force in magnitude with opposite direction is the force that object 2 is exerting on object 1, then the resultant of those two forces will be equal to 0, wouldn't it? So 10 meters, if we say 10 newtons east plus 10 newtons west, the force net of those will be 0. But the object is still moving. So why do you think that the object is still moving? Because if it was not, then force net will be 0. Therefore, acceleration will be 0. The object will not be moving. However, we know that if we push an object, then this object will be moving. Why is that the object is moving when we see that those action or reaction or this law is in place. I just want you to think about it for 1 second, and that's the reason that those two forces do not cancel each other, to create that is called force net zero, so that the object is not moving. It's because those two forces are in two different objects. So it's force 1 exerted on object 2, and then object 2 exert a force on object 1. So the forces will cancel out only if they are happening on the same object. But if there are two different objects, then those forces do not cancel out. Does this make sense? Okay, so now we have two graphs. Acceleration, force net, acceleration, force net. And the mass of the object that we are dealing with, it's, let's suppose, 500 grams, which in international system unit will be a 5.0 times 10 to the power of -3 kilograms, or 0.5 kilograms. Both of them are fine for the purposes of this question. So now, if I'm telling you that this is the graph, the acceleration force net graph that you see, first of all, what is the slope of this graph? Okay, so when you calculate the slope, guys, you go delta y over delta x, whatever is your delta y. Delta A is, in our case, over delta F net in our case, okay? Which is A2 minus A1 over F1 over F2 minus F1. But what we are trying to figure out here is what is the physical quantity that the slope on this case represents, which means that the clue for this will be from the units. So the units of acceleration are meters per second squared. And the units for force are newtons, which we can say that are kilograms meters per second squared. So now meters per second squared and meters per second squared is canceled out, and it is 1 over kilogram. So the slope on this case, when A is in the vertical axis and F net is on the horizontal axis, is represented by, or it's representing 1 over mass of the object. So it's the inverse mass of the object. If we had the situation that in the y-axis we have F net and in the x-axis we had A, then what we would see is that the slope, you can see that in your calculation, delta y over delta x over delta x. Our delta y is force net, so delta F net over delta A. The units for F net are the same as the units for forces are kilograms meters per second squared over meters per second squared. So meters per second squared and meters per second squared are canceled out, and then we are left with kilograms. So on this case, when we flip the axis, when we switch the axis, the slope will represent the mass of the object. Is this clear? So let's go back to the question now. We have a 0.5 kilogram, and then we have a force net of 1. What is this value here? Answers on the chat, please. So on the chart, you were saying that this value here is 2 meters per second squared. Why? Because force net is equal to mass times acceleration. And when we find acceleration is force net over mass, which will be 1 in our situation for the first case, over 0.5 is equal to 2.0 meters per second squared. So this will be 2.0. And on the case when we have 2, I was going 2 force net, then acceleration will be, what is this value here on the chart, please? Yes, 4 meters per second squared. And now let's take a look at the other one. When we have, again, the mass is 0.5 kilograms, and then what we have is, as a given, is acceleration. The calculations that you will do on this case will be, force net, sorry, we are looking for force net here. So force net will be mass times acceleration. So mass is 0.5, then will be 0.5 times 3.0. So the value of the force net here will be 1.5 newtons. And on the case when we have the 6, the value of the force net will be 3.0 newtons.